Okay, so here that is thin film hybrid circuit. So in the MIC, there are MMIC, that is monolithic and hybrid. In the hybrid, there are two technology. One is the thin film, other is the thick film. That also we are going to try to complete it today. So in the thin film, in the hybrid technology, these are the fabrication processes. In the last lecture, we have finished the first point, that is the circuit construction material specifications. So this we have discussed, that is for the substrate, for the conductor, and for the resistor, capacitor. What is the specific, you can say, the material specification, what material we are using, that we discussed. Now we are going for the technology selection. Now in the technology selection, here there are some, how, what are the technologies are there. So here there are mainly two technology, that is the NICR AU SIO technology and titanium technology. So technology requirement, why we require technology, that is the easy production and compatibility for the material what we have selected, and the avoidance of the unnecessary difficulties. So whatever the difficulties are there, so that difficulty should we avoid. Then circuit requirements. So whatever the circuit you are going to fabricate, what are their requirements, that also be there. So based on that, these are two technologies we are going to discuss: NICR AU SIO technology. These are the materials, so it is called this technology, and second is the titanium technology. So what is this NICR AU SIO technology? NICR uses the resistive layer. So here, as we discussed previously, resistance, capacitance, and the conductor layer. So that mainly we are doing this, and the semiconductor, whatever the semiconductor components are there, as it is the hybrid technology, semiconductor material that we are doing connecting externally. This is what the thing that I have to mention here. So these are the small parametric variation with the temperature with this NICR, and so that the copper layer is used to evaporate on the NICR. So this way it is used. Also here a gold, that is AU. So the gold layer is replaced by 5 to 10 micrometer thick copper layer. Okay, so the intention of the gold is generally it is proof to the deoxidation. So it doesn't take corrosion or the oxidization. So that's why we are using this. And then the next is on copper layer, 1 to 2 micrometer thick gold layer is deposited. This is what I am saying, that the other silver or the copper, they may have the corrosion or the oxidation, but here on the gold, this can be avoided. So 1 to 2 micrometer layer thickness is used here. So this is what the technology, how it has fabricated. So here this is what the circuit, and lower is the fabricated material. So this is, you can easily understand. This is what your conductor. This is resistor. Again conductor, between these two resistor, conductor is there. This is capacitor, and again conductor. So resistor and capacitor are connected in series. How it can be fabricated? So you just see here, whatever this dot dot, whatever the lower surface, it is the substrate. So you can have the specific substrate as we have discussed in the material. Okay. Now the very first is the conductor. So how conductor layer is there? So here the conductor, you can have the two layer. So below on the substrate you will have a very thin layer of, what is this, the resistance of adhesive layer. So it is NICR. So this is what NICR layer. So whatever the substrate you are using, NICR layer of 0.02 micrometer thick, and with RF equals to 50. So this layer, on this layer we are doing the fabrication. Okay, so this is for the register. Okay, this the black layer, it is for the register. So this is whatever this register is fabricated, it is fabricated on this NICR layer. Okay, so for the resistance, NICR layer is used. And for the conductor, here the conductive layer, this is what the cross line, it is the conductive layer. And in the conductive layer, what you can say, the conductive layer, uh, electroplated gold, that thickness is 5 to 10 micrometer thick. So the 5 to 10 micrometer thick the gold electroplated, and below that evaporated gold or the copper with 0.3 micrometer thickness. Okay, so below that you will have this. So this is what your conductor. Now after conductor, as I explained, this resistive material NICR is used for the resistor. Again this conductor is here, again the same layer is here. Okay, but it is connected to the capacitor. So the capacitor lead, so you can say this capacitor lead, that is the aluminum lead, it is there. So it is connected to the this conductor. Okay, here this is connected to the conductor. And this the black, what is this black portion, this is what the capacitor dielectric, it is evaporate, that is SiO. Okay, SiO film, that is having the epsilon R6, and the loss tangent is very less as compared to, that is tan delta is 0.01. And SiO2 or Al2O3 is also the alternative, but as this is what the substrate, so this substrate is used, and this another. So what this technology, we can say NICR, whatever the NICR is here, it is used for the resistance register, whatever the register we require for the resistance. Here it is shown SiO, it is a dielectric material, that is for the capacitor. Au is the gold, and it is the gold plating is used. So that's why this is what the major component. So this technology is called NICR AU SiO technology. Okay. So in this is what the previous technology. This is a brief understanding. Now we will go for the titanium technology. Obviously what the material used will be the titanium. Okay, so titanium material is used for as a resistive layer, whatever the resistive layer is here, so that can be there. So titanium nitrate is also used for high surface resistance of 10 to 100 ohm, if you require the high surface resistance. Titanium peroxide is very good dielectric use in the titanium electrolytic capacitor. So titanium is used for the resistance, and titanium peroxide is used for the dielectric. So the technology is obviously the titanium technology. So what material we are using, it decides the technology. And gold, obviously here gold is mostly the default used for the conductor material, which is produced electromechanically on NICR layer. So similarly, the resistance can be adjusted to correct value by the what this anode oxide for the titanium layer. Okay, so this is what, to reduce the series resistance of the capacitor, the TA basic electrode is deposited on the aluminum layer. So this is what the pressure here, the this is what the detail little bit for the substrate and the fabrication. So what will be the pressure and the temperature here. Okay, as the previous, this is what again the same circuit, that is what the conductor, resistor, conductor, capacitor and conductor, how it is fabricated. As I explained previously, here we are mainly having the resistor and the capacitor in the circuit, that is on chip, that is on the substrate. Integration of resistors and capacitor will be done. All the other material, that is the semiconductor material or the semiconductor ICs, in terms of the diode, transistor or any other semiconductor that are kept, that are mounted externally as a hybrid component. So here, as the previous, you can see in detail, the conductor layer is the gold. Again, the conductor layer 5 to 10 micrometer thickness. These are the general standards. Okay. Now, in this titanium technology, this is what the circuit we discuss, and in this circuit, whatever the selection is there, according to the selection of the material. So titanium is used for the resistive layer, and titanium peroxide is used for the capacitive dielectric material. So same thing is used here. You can see here in detail. Now we will go for the next. Okay. Now we will go for the third step. Now the technology selection we did, and apart from the technology selection, this third is the procedure sequence. Means now we have to go for the fabrication, the batch process, or how we can fabricate it. So these are the four steps for the fabrication, and one by one we will go for the fabrication step. And in the fabrication we have the photomask production. So as this is the mass production, so how photomask is produced, then structure fabrication, then the adjustment of the component value or the circuit if it is required, and then insertion of the hybrid element. As I told here, the hybrid element, that is the semiconductor material, is not integrated in the this hybrid technology. So whatever the semiconductor diode, transistor, or any other that are externally fabricated, this is comparatively the old technology. Nowadays generally it is not used, maybe on some component, some circuits it can be used, but generally MMICs are used nowadays. Okay, but still we have to understand how this is there. So what I'll request, uh, anyone is there? Atul is there, or someone, Mishra, can you read this? Now you can start.
Production sequence. Before vapor deposition or sputtering on the substrate, the holes for the through contact must be drilled to ensure metallization through the holes. A pre-aging, example 1 week at 125 degrees Celsius, is only needed when many unpacked semiconductor elements are used in the circuit. Circuits are often prepared in large quantities, whereby many single circuits are produced simultaneously on a large substrate. Example, area 4 into area 4 by 4. After the hybrid elements have been added, the circuits are separated from one another.
Okay, this is what the simply, if you will read this, that you can understand. So that's why I request him to read this. Okay, so the main thing is what, it is a complete batch process, and generally the area for one substrate is taken 4 by 4 inch by 4 inch, and whatever, irrespective of whatever the size of your circuit, some PCBs are of that shape. Maybe in 4 by 4 you may have the 16 PCB or more, but irrespective of that, generally in this area the multiple PCBs are kept, and after doing all the processes and putting all the hybrid element, then it is cut and given it to the separate part. This is what the procedure, this mainly we are going to discuss. So on the left side you will have the substrate. You take a substrate and do the substrate preparation, that is polishing and all these things, and put a evaporation or sputtering. What is this evaporation or sputtering? That we'll discuss after this. This thickness layer is put, and here this is what your fabrication machine on the right hand side, or the fabrication mechanism what you are using, that we are using here. So the photo mask production or these things that can be done. Then you can have the uh, structure production, that is the photolithographic method. What is that? These words you are familiar. So when we'll go, you will adjust, you will understand. Then adjustment of the component, maybe the register or the other, how you can do the adjustment means the accurate value how you can get. Then hybrid, whatever the hybridization, the whatever the external component, how you can put here. Here in the hybridization, capacitor is also mentioned. In the circuit, the capacitor values are sometimes limited. So if it is required for the high voltage capacitor, that can be also externally hybridized. Then the other process, then the system adjustment is done, and packaging and the final testing. So this is what the block diagram, this we are going to understand right now. So what is the important thing that we discuss here now. Here, as the four step are there, so we will go one by one. That is, very first is the photo mask production. As this is the preparation on the right hand side, what it is mentioned. So photo mask production, how can be done? Now read this. Same, same student, roll number 21. You just
So
read
25.
throughout the end. You are
Uh,
25, na? What you
yes,
are
sir.
reading?
20.
Oh, read it.
Photomask, photomask production. Photomasks, photomasks are film or glass plates upon which the required conductor structure is produced as a negative in size ratio 1:1 with high precision errors in general less than 1 to 5 micrometer. Batches of masks are required for the photolithographic production of a complete circuit. The photomask can be produced manually or automatically.
Okay. So this photo mask negative is prepared. Sometimes it is in the ratio of 10 as to 1, but here it is mentioned the size is 1 as to 1, means whatever the size is there. The generally what error we can get, or the accuracy, you can say 1 to 5 micrometer. So accordingly the track size and all this selection that we have to do. And it is the batch process. So how one after another it has been done. So that is called the batch process. Then this next, read this. Yes, you read this.
In photomask production manual. In manual production of photomask, the required conductor structure or layout is generally in 10 times the scale. A coordinate graph is used, which is a workbench with a knife that can precisely move into coordinates to an accuracy of plus minus 20 micrometer. The double foil consists of a clear foil and an almost opaque red foil. The red foil is cut out from around the required layout. This is then photographically reduced by a factor of 10 to produce the photo mask with an accuracy of plus minus 2 micrometer. The original can also be produced manually without the coordinate graph, accuracy of plus minus 0.2 mm.
Okay. Now, what is two things are here? The coordinate graph is used, means whatever your structure is there, below that a graph is used, and the graph is having what you can say, whatever the graph structure is there. Now, when you will prepare the whatever the layout, so in the layout, what is the scale here? As I mentioned previously, the scale is increased 10 times. Suppose you will have 1 micrometer by 1 micrometer any component, so it can enlarge to 10 micrometer because it is easy. This is the manual process. This photomask production manual. So this is the procedure for the manual production. So generally the screen or something is used in the manual process, and so that's why in the manual process we are not able to work accurately on the micrometer scale. So the scale is enlarged 10 times, and then it has been worked out, and again it has been reduced, that is by the scale of factor of 10, and can be used. So here the if you will use the graph, so your accuracy is better. If you will not, then accuracy is comparatively lesser. The 100 times error will increase if you will not use this graph. So if with graph, you will have the plus minus 2 micrometer accuracy. Without that, plus minus 2 mm accuracy. So it is very raw method without the graph. Okay. Next, read this.
Photomask production automatic. For the automatic computer aided production of photomask, A mass generator, sometimes referred to as a pattern generator, is used to create photomass of the correct size. This machine generates the total mass structure from a large number of light flashes at predetermined position, accuracy better than 1 micrometer. The complicated drive commands for the light generator movement and aperture size are stored on magnetic tape.
Okay, so here automatically how we can generate, it has the better accuracy, that is 1 micrometer, means 2 times better than the previous. And this is what, no need to, on the same scale we can have the generation in the automatic photomask. Next, read this.
This command tape is in turn produced in a computer using a mass generator program. This program translates the engineer mass design at the graphic display terminal into commands for the pattern generator. Basic store of standard structures such as right angles, circles, curve, triangles, etc. etc. is available at the terminal and can be used to assemble the mass layout.
So this is what the general procedure, that how it can be done, and this way the photo mask in the automatic manner is done. Now the photo mask manual and automatic that we have discussed. Now we will go for the right hand side, whatever the block diagram on the right hand side that we discuss how. Now the structure fabrication. Now we will go for the fabrication, that is the whatever the substrate and structure we are fabricating, whatever the structure is there that we are fabricating here. Now read this.
Structure fabrication. Structure fabrication include only strip conductors and resistors without integrating capacitors. The conducting material layers are deposited on the substrate by vapor deposition or sputtering technique. Both deposition technique require vacuum pressure of 10 to minus 6 torr to 10 to minus 2 torr. This is achieved by a vacuum pump connected to bell jar, the container.
Okay, now we are going for the fabrication, the actual fabrication process. Whatever the structure is there, how it can be fabricated. So this two methods, sputtering or you can say the vapor deposition. These both the method we are discussing. You might be familiar about that. Now here they are done in a vacuum with a pressure of 10 to the power minus 6 or 10 to the power to the 10 to the power minus 2. This torque for every method is different, the pressure is different, that we'll discuss. And the vacuum pump, the vapor is deposited. Here you can say the conductor and the resistor layer are only fabricated in this. Integration of the capacitor is done afterward. Okay, so this is for conductor and the resistors. Now we will go for this. So this is what very first, that is the vapor deposition. Now in the vapor deposition, what is the thing here? So before we will go here, you just focus on the diagram. So in the diagram, you will have here whatever the substrate, it is kept on this hold. This is what substrate holder, and here the substrate is kept, whatever the lines are there. The material vapor source, whatever the deposition you have to put, that is kept here, that is in this, you can say it is a boat. Okay, this boat like structure. So this is the material is kept here, and this will evaporate the whatever here the system is there, and it has been given electric heating, and this it get evaporate. Before doing its evaporation, this vacuum pump give the required torque. So for this vapor deposition, you will have a torque of 10 to the power minus 6 torque. That is the pressure, air pressure, vacuum pressure. That is the negative pressure is required. And when this the whatever the vapor is deposited here, the vapor it will go and it will deposit on the substrate. For the time, you can control whatever the thickness of this vapor deposition is required, and according to this shape of this holder, because this will go and only hold only make on this surface, and whatever the restricted area, it will not go there. So accordingly, this holder can be designed according to the circuit requirement, and then this is done. So the same thing is explained here. So continuously you can read this complete.
The material to be deposited is placed in a container boat. The container can be electrically heated and has a melting point. well above the evaporation temperature of the contents. Boards are usually made up of molybdenum or tungsten. High vacuum pressures below 10 raised to minus 6 torr is required. The board temperature is raised to around 1000 degrees Celsius. The material evaporates and propagates in a straight line, deposits on the substrate. The container is filled with argon at a pressure of approximately 10 raised to minus 3 torr.
Okay.
Two electrodes.
Just wait. Now this is vapor deposition is done. Now we are in a sputtering. This is what the second method. Vapor deposition is one method and sputtering is the another method. Now here whatever the diagram is same for the sputtering. Again the vacuum is created, but here the vacuum pressure is comparatively less. It is the argon gas. We know the inert gas we have studied in the high school level. So this argon is given inside, and the argon pressure is 10 to the power minus 3 torr. Okay, this will be the pressure that we have to maintain. Now this is what the ionization method. So that also we know discuss in the chemistry. So here this is what the cathode and the anode. So this is what cathode and anode, and whatever the things are there, the cathode and anode, and here the substrate is kept. Okay, so here your substrate is kept. So substrate is here, and the ionization techniques on the substrate, it get deposited. Okay, and the pressure here is comparatively less because the ionization method we are using, so it is called sputtering. So this is what the detail about this. Now you read. You can
The
read.
container,
Uh,
the container is filled with argon at a pressure of approximately 10 raised to minus 3 torr. Two electrodes, anode and cathode, produce a gas discharge. When a potential difference of several thousand volts is applied due to plasma of argon plus ions, these ions are accelerated to the cathode target, which is made of the material for evaporation. The ion energy is sufficient to release atoms from the target, which in turn deposit on the substrate situated adjacent to the anode. Due to the very low deposition rate of evaporation and sputtering, the thickness of the adhesive layer and the initial conductive layer are between 0.01 micrometer and 1 micrometer. The required thickness of the conducting layer is around 10 micrometer, which is deposited electrolytically on the initial conducting layer. At this stage, the substrate is completely metallized.
Okay, if you require the layer of 0.01 micrometer to 1 micrometer, then sputtering is used. Okay, next.
Create the create the conducting structure. If a photoetching method, photolithography, is used.
Okay, so this is regarding the this sputtering. Okay, structure fabrication. Now here photolithography is the next method. Again, so in the photolithography there are positive photolithography and negative photolithography. So what is that? What do you mean by positive one? Next. Read this.
Uh, Negative method requires the region of the conductor pattern on the photomass to remain translucent while blackening the conductor-free regions. The whole surface is covered with photoresist and exposed through the mass. After development of the photoresist, the exposed areas are washed away and then the metal on the uncovered areas is removed by etching. The required conductor structure remains.
So this is what negative photolithography. You people know this, how it can work, and positive photolithography. How, what is that?
The conducting regions on the photomass are blackened and the exposed areas can be removed after development. The metallization areas freed of photoresist are removed as before.
Okay, so this is positive and negative photolithography. And this is what the structure of the photolithography. It is shown here. The photoresist material is developed and how it can be resist this. It is resisting, so this portion will remain and the other is get each. So this is what the one process is photolithography, and this after etching this is done. So this is what the simple process. Next.
Uh, initially, the Initially, the whole substrate is deposited with 0.05 micrometer to zero point 0.1 micrometer of adhesive and conductive layers, following which photoresist is deposited and exposed through the photomask. The exposure, the photoresist or the conducting area is washed out, leaving steep walls of photoresist approximately 10 micrometer high. Conductive materials, gold or copper, is now deposited electrically in the areas freed from photoresist, attaining thickness between 5 micrometer and 10 micrometer, with a profile accuracy of 3 micrometer to 10 micrometer.
So this is galvanic technique, thickening. Next.
Initially, the whole substrate
No, no,
is
no. Last line.
deposited.
Last line. Last line.
Finally, the remaining photoresist and the thin adhesive and initial layers between the conductors are etched away.
So this is what the third process, that is galvanic thickening. So this way it can be done. Okay. So this is what the way is done here. So three structure fabrication we have done. Now the adjustment. So this adjustment we are going. So this adjustment is very minute thing, that whatever the adjustment we have to do in this. So here the component adjustment and the system adjustment, two things are there. So here the examples, that the register value, how the adjustment is done, and that we are going to discuss. Read this.
Component adjustment. Component adjustment signifies the change in a specified component value. Example, a thin film resistor. System adjustment. System adjustment uses a single component to obtain a given circuit performance. Example, the gain of a transistor amplifier or the loss of an attenuator. System adjustment is generally more costly due to test equipment, etc., and the fact that many elements play a role in system performance.
Okay. So these component level adjustment and the complete system adjustment. So complete system adjustment is costly because we require various system performance. Component adjustment means whatever the component, suppose a register you have made. So whether this register is giving that proper value or not. And system adjustment means whatever the system you made, whether it is functioning at that required performance level or not. So here you require certain equipment on all this. So component adjustment of the thin film register that we are going to discuss. So if you have fabricated the thin film register, then how it can be done? Read this.
Perpendicular cuts to the current flow for rough adjustment. Fine adjustment is achieved by cutting along the direction of current flow. The slots increase capacitive parasitic. To avoid this anodic oxidation for tantalum resistance, a bridging of resistor section can be used.
Okay, so here the fine cuts are made. That is what the film register, and this fine cut, how it is made. So it is shown here. So these are the some techniques. You can say 7 8 techniques are shown here. So these are the techniques that. So what is this? This is what the current flow. This is what the current flow, and in this direction you made a cut. For what? The register value adjustment. Whatever the registers value, that we have to adjust. And here you can have the L shape cut, and accordingly require, it depends on the, suppose your register value is high or low, accordingly we can have this cut. And to adjust the value, this is what the fine tuning method. So these tuning methods can be used here. So these are the methods that you can, while doing your the, what you can say, design of your project on the PCB. This is required. If you will have a track with high resistance, so you can do this cut and accordingly the resistance can be adjusted. So here the other methods are there, and this is what the meander cutting. So this structure here in a meander structure it is done. Okay, so there are various methods depending upon the requirement that can be done. So these are the examples. Then adjustment of the stripline conductor. So if you will have a stripline conductor, then how you can do the adjustment of that? So here you can have the strip extension on the open circuit with a bridge. So this way, with a bridge you can do the extension, or the continuous shortening of an open circuit by layer, by removing this layer. So this way these methods are there, and strip uh, reduction of the what you can say, the spiral inductor with a bridge. So this is what you can say, the spiral inductor is there. So with this bridge you can have this what you can say, this you can short this two element. So this way the conductor adjustment can be done to adjust their parameter. So this is what the adjustment is done. And the last point in the production sequence, that is the third part, is the, this is what, insertion of the hybrid element. Now whatever the other hybrid element that we have to insert, so how we can insert this hybrid element? So in the most common application of the thin film hybrid circuit, only resistors are integrated, that is the capacitors are included as a hybrid element in the same way as the diode and transistor. So sometimes capacitor, diode and transistor are used as the hybrid element. So these are the various methods that how it can be used. So here the first A diagram, here the diode chip is shown here. So the diode chip is put here. Then the next is your transistor chip. So this B, this is what the diagram here, the transistor chip is put as the hybrid element. Then these are some other element, one by one, the diode, transistor and the other, they are kept. So you can see the diagram, and the diagrams are the self-explanatory. So you can see this. Then insertion of the hybrid element. These are the some fixed capacitance, their values. You can have these specification depending upon the value, because when you will fabricate, when you will design, you have to keep in mind that is which value components are available. So this is what the understanding of that, this is the fixed capacitor. In this technology, in this way system, these capacitors of these particular values are available. In capacitance, the capacitance value is also given, as well as their voltages are also given. Variable capacitor, some application we require a variable capacitor, so these are also there. So these are some specific values. Then fixed registers. So thin film chip, we can have the register from 10 ohm to 560 ohm, can be fabricated of what, 1/8 watt. So this is what power handling capacity of this register. Then thick film, in thick film, the value of the register that will be higher, up to 10 mega ohm. This is 560 kilo ohm only, but here that is the 10 mega ohm can be done. Variable register is also possible. The fixed inductors, that is, these are the all hybrid element that you can include. Okay, so variable inductors externally you can include. Inductors initially that were not fabricated in this size, it was difficult. Nowadays in the advanced technology there are some limit, with some limitation is possible, but still the inductors are taken as a hybrid element. And these are some diodes. So whatever the pin diode and the other diode, LED, that can be put. Transistors, so all type of transistor, up to 2 gigahertz the transistors are working, so that can be also fabricated here. And insertion of the hybrid element, these are the techniques. So you read this. Yes, you can read this.
The most important methods is soft soldering at temperature between 200 degrees Celsius and 250 degrees Celsius. By the insertion of individual elements, the substrate is preheated on a hot plate, and the remaining heat is applied by infrared radiation or from a beam of heated gas. All components can be inserted at the same time by placing a shoulder perform or paste on the circuit and heating in a continuously heating oven.
So these are the specification. In general, we can say simple soldering technique. You can do this, and these are some processes, mathematic processes also there. So the temperature is also maintained 200 to 250 degrees centigrade. So these are the techniques. This is what the these are three four techniques for the different component bonding and the alloying, and this way we can have the hybrid. You can put the hybrid element in the system. Okay, so this is for the soft soldering. All fixed capacitor, variable resistors, and diode and transistor by soft soldering, and the attachment with conductive coil. So fixed capacitor, variable resistors, fixed resistors, diode, and transistor can be done by this method. So it is the limitation or the particular method is used for the particular system or the component. And here allowing this for the and ultrasonic bonding and the thermocompression bonding. So these materials or these systems are used. So these are their specification. So this is what the whatever we discussed about the thick film. Now, sorry, thin film we have discussed. Now this is a thick film hybrid circuit. Now two topics are the this is thick film. It is remained. So that we'll discuss in the next lecture. So right now we will stop here.